Hello and welcome. In this video, we'll summarize details for a solar oven data logger developed by Pima Community College students and myself, supporting the Innovative Education for Solar Technicians and Engineers program, or IESTE. This program was started thanks to a presidential executive order focused on realizing carbon pollution-free electricity by 2030, specifically by providing student training in solar technologies for the purpose of growing the solar energy workforce. Interns from both the University of Arizona and Pima Community College were recruited and spent the summer of 2024 working on various projects in support of the same. In addition, students affiliated with Pima Community College's Advanced Manufacturing Club were invited to volunteer and support the project. The solar oven data logger summarized in this video came out of this coordination. So what exactly is a solar oven data logger? Well, during the design and testing phase of various solar ovens, it was necessary to take readings of temperature and incident solar power to understand design limitations and efficiencies. The challenge, of course, is that these are instantaneous measurements requiring continuous monitoring and plotting by students, and thus not particularly efficient. This presented us with an opportunity for doing things better. We also consulted with seasoned solar oven enthusiasts like Katie Garmany regarding what kind of improvements she would like to see in conventional setups. After sharing some wonderful cornbread made in her solar oven, Katie noted it would be helpful to have a better means of monitoring temperature in the oven, perhaps an improved display for reading temperature in real time. In response, we explored open source hardware and software for building a solar oven temperature logger that could record data for import to a spreadsheet, display temperatures instantaneously, and present graphs for understanding heating or cooling dynamics over time. Open source alternatives make royalty-free platforms available to makers innovating in science and technology, with hardware options available through electronic vendors such as Adafruit and SparkFun. Our data logger takes advantage of the same by coupling an Adafruit Feather MO data logger with a DS3231 real-time clock, both of which rely on open source libraries for programming. This hardware combination gives us an inexpensive means to collect and write temperature data to an SD card in comma delimited format, which can be read by a spreadsheet. The real-time clock gives us a means to timestamp data collected by our temperature sensor over time. We coupled our data logger with a K-type thermocouple commonly used in conventional ovens. We started with this model sold by Adafruit, which includes a fiberglass sheath for operating in high-temperature environments, as well as a stainless steel probe on the other end. This thermocouple can measure temperatures of up to 932 degrees Fahrenheit. The signal generated by the thermocouple is on the order of millivolts, so we coupled the sensor with an amplifier so that signals could be interpreted by a microcontroller. Finally, we added a 3.5-inch TFT display for both displaying data in real time while generating graphs, and a small protoboard to help us tie everything together with respect to wiring. An optional item for remote deployments was this LiPo battery, which gives us the means to take our data logger on the road without need for an electrical outlet. Fortunately, the software libraries required to drive all these components may be downloaded via the Arduino Integrated Development Environment, or IDE, and then customized in an Arduino sketch, which can be uploaded to our microcontroller. Associated libraries are freely available thanks to the generosity of the open source community, as well as Adafruit, an electronics vendor which does an excellent job of documenting and supporting the hardware that it sells. We even managed to find code for graphing data to our 3.5-inch TFT screen thanks to this individual who freely developed, published, and explains his code on YouTube. Regarding wiring, the Feather MO data logger and the real-time clock plug in directly into one another, and then seat directly on our 3.5-inch TFT screen via these female socket headers on the back of the display. This image shows how the remainder of the wiring is addressed between the screen, the thermocouple amplifier, and the thermocouple itself, which communicates over a protocol known as I2C with the microcontroller. This image shows how everything is wired up in our own setup using a protoboard and terminal block to facilitate connections between the thermocouple, the amplifier, and our TFT screen. Overall, this hardware combination gives us the ability to assemble, document, fully customize, and add additional sensors to a solar oven data logger at very low cost, relative to what a commercial data logger with similar capabilities might cost. More importantly, since our design is open source, it may be shared, used, and continuously improved by others for applications requiring continuous environmental monitoring. After various iterations and improvements, we ended up with this first prototype housed in a cardboard box. And this is us setting up the system for our first test in one of our first homemade solar ovens. The prototype both displays instantaneous temperature readings and graphs that may be customized in code. We then downloaded the data off a camera SD card that was originally seeded in our data logger and imported it seamlessly into Excel for graphing. And here are the graphed results of our first test. You can see that this graph allows us to understand that it takes about 2 hours for the solar oven to reach about 90% of its maximum temperature. It also gives us an idea of the impact that opening the oven can have. And finally, you can see that it takes about 30 minutes for the oven to cool 170 degrees, from about 260 degrees Fahrenheit down to about 90 degrees Fahrenheit. Although our first test was successful, subsequent experiments helped us identify some weaknesses in our setup. Specifically, we learned that proper signal processing requires a tight connection between the thermocouple leads and the amplifier. The tiny leads associated with our original thermocouple were not ideal for this. And one of the issues I see with this setup is this little thermocouple has a really slow response time. It just doesn't keep up with rapid temperature fluctuations. And I think it has to do with the fact that the connections in this little terminal block are not really tight, because when I wiggle this around, it responds quite quickly. We also learned that it helps to have a more robust waterproof sensor to measure temperature in liquid environments. In response to these challenges, we eventually upgraded our thermocouple to this model. This has a more robust sensor housing and better terminals for tying things together, in addition to a 2-meter stainless steel sheath for being able to stand away from the solar oven while taking measurements. We also picked up this hinged clear cover ABS project box, which makes our data logger a little bit more robust with respect to field conditions. And finally, our local makerspace donated one of these terminal blocks, which really helps improve the connectivity between the thermocouple and the thermocouple amplifier. With those improvements in hand, this is our latest prototype, showing our original hardware embedded in an IP67 rated weatherproof enclosure. And finally, here's our improved thermocouple, which is fed into the box via a waterproof gland. And here's a graph of our first test of the improved hardware and some code revisions that we were experimenting with. And here you can see that we went ahead and we placed the probe in a glass of ice water, and that yielded a temperature of about 36 degrees Fahrenheit. We then poured some boiling water over the probe in a cup, and that raised the temperature to about 191 degrees Fahrenheit. And then to really understand the accuracy of the probe, we put it directly in a pot of boiling water, and that yielded a temperature of about 212 degrees Fahrenheit. And the interesting thing between the low and the high measurements is they're off by about 4 degrees, which is about right for the reported accuracy of this probe. Regardless, doing this experiment allows us to essentially calibrate that probe in our code simply by subtracting 4 degrees Fahrenheit from the measured temperatures. So in this part of the video, I'll briefly go over the code that drives all this hardware and the display, for which I'll include a link in the description of this video so you can download and play with it, modify it, improve it on your own. And to be clear, this code is written specifically for the hardware that's already been described in this video, and respective details are called out in the comments section at the top of the sketch. Now, for those of you who are new to Arduino, I'll go ahead and include links to all the hardware that's called out in this video, specifically the learning sections that have been prepared by Adafruit, which are most excellent and should get you up and running pretty quickly with respect to setting up your Arduino IDE, identifying libraries that need to be installed in the IDE so that your code compiles, and just getting you on the right foot so that everything works by the time you've got your data logger put together and you're ready to upload that code. And near the top of the sketch, you'll notice that I have a suite of libraries that are called out to basically drive that hardware that you're using for your data logger. If you go through the setup procedures that are explained in Adafruit's learning sections, these libraries should be easy to include and should compile correctly when you're ready to upload your code. Now, what I've done to make this code easy to modify by you is I've defined some variables near the top of the code in this section called Global Variables to assist with fast graph and log editing. And I'll go over respective variables right now. The first three variables are basically the graph title, the X title, and the Y title. So in this case, they're identified as sensor temperature, delay step, and temperature in degrees Fahrenheit. And then you'll notice that we also have this X inc and Y inc, short for X increment and Y increment. And all this does is basically give you an option to modify the spacing between the graph lines on the data logger. Play with this a little bit, you'll get a feel for it, but changing those numbers will basically modify the spacing between your X and Y lines on your graph. Next, you'll see that we have this log right variable, and what this does is define the array size for collecting temperatures and for graphing. So as currently set at 20, what that means is 20 temperatures are going to be collected and displayed graphically on the screen. Next, we have this log delay variable, which is currently set to 2500 milliseconds. So what this variable does is it sets the delay in milliseconds. So in this case, 2500 milliseconds would be 2.5 seconds between subsequent temperature readings. So if I have, let's see, I've got my log write set to 20 and my log delay is set to 2500, it's going to take 20 readings, but each reading is going to take 2.5 seconds before the next reading is inserted into that array. So that's just a way of kind of like controlling the rate that data is coming in and being logged and prepared for your graphical interface. And finally, we have this graph delay variable that's currently set to 7500 milliseconds. That means that once the graph has fully drawn, it's just going to hold that graph in the display for 7500 milliseconds or 7.5 seconds so that you can review it, you can make notes about it, etc., before the whole process starts all over again and temperature starts to get logged for the next graph display. And that pretty much sums it up. Those are the only variables you really have to modify for your specific needs. This area that's highlighted right here just basically contains some notes regarding my own test, what works, what's given me some challenges. But if you stick within these parameters, you should just be fine. The data logger will work well over time. So that just about does it for this brief introduction and summary of the solar data logger developed for this project. In a future chapter, we'll talk a little bit about a spreadsheet that we developed that, when coupled with data collected by this solar data logger, can be used to understand the CO2 offsets associated with heating or boiling water in a solar oven versus using conventional fuels like coal or wood or natural gas or electricity. So that's a whole different chapter. We'll talk about that soon. In the interim, I appreciate you watching this video. Please give us a thumbs up if you found this interesting and consider subscribing for updates. Thanks.